Okay, in this tutorial, we're going to be I'm going to show you how to get a graph out for our shear force diagram and our bending moment diagram for the assessment task question. If all works well, we should get some sort of diagram that looks similar to this for our shear force diagram, and we'll get some sort of diagram that looks like this for our bending moment diagram. This is assuming you've already done all the maths associated to find um, the components for this graph. So what you'll need at this point for us to start is you're going to need the length of your wing, which you find by your student number, WE, which is the location of where the engine is. Yeah, WE, which is the location for how far away the engine is from the center of the aircraft. W, which is your weight value. Now that's in newtons there, so it's the mass times gravity. Um, Engine percentage is how much percentage of that weight is the engines. So 19%, both engines combined is 19% of the weight. The lift of the tail is how much the tail is pushing down. And the wing, that should be our distributed load along the wing. I have it there in newtons per meter. You could have it in another unit if you need it like kilonewtons per meter. But that is our distributed load. That is enough for us to start. Now, if we look at my other graph over here, I went a bit overboard and I did it to like 1,000 different units. I'm just going to do a simple one. We'll do it to 100 so we don't have to drag down as much. So we know we're going to have a number here. This will be our, we'll call it our distance. This is from left tip. This is going to be our distance from the left tip of the wing. So we're going to start at 0, and we know if we go down 100 units, we're going to end up at, if one of our wings is 5.88, we're going to get to twice 5.88 as our unit. How we're going to do this through a spreadsheet software is we want each incremental step to happen here to be 1/100th of 588 times 2. So this will be, we can use the formula, we can press the equals button, and we're going to write a formula here. We want this to be 588, so we press cell B2, multiplies by 2, so that's the total length of both the wings, divided by 100, and that's how much each step is going to be. Now, if I try to drag this down, it's not going to work. So just a reminder, things in Excel or spreadsheets, if we look over here, we see this over here is highlighted in yellow. If I try to drag this cell down, it's now dragging the cell below it. So we have to lock it in position so when we drag it down, it doesn't move. So we'll go back to this original formula, and we have to put dollar signs in front of both the B and the C. And what the dollar signs do is it locks it in place. There's also a shortcut for this. If you don't want to press the dollar signs, if you press F4, it cycles through the different versions of that. So if you press F4 once, it locks in both the columns and the rows. So it locks in the B and the C. If you press F4 again, then it's saying, I just want the rows to be locked in. So you can drag it to the side. You can drag it and the letters will change. Can I? I'll try. Hold on. There you go. Does that work? So that's just, if you press F, and if you press it, I pressed it a second time, it just the B is locked in, so it's going to keep the column, but the rows will change, and you're cycling through all those as you keep pressing F4. For this case, I want to lock in both the B, I want to lock in the column and the row. So when I press Enter here and I drag this down, I think I need to just do a balance of so if I try to drag this down now, we should get the same distance. So now every step is going to be 0.11 of a meter. But we eventually want to get to whatever, 12, 11 distance. So how we will do this is, we want this formula to actually plus the previous value. And now if we drag this down, we get this numbers increasing, and that's our distance. And if we look on the very left, we have the row. So right now we're in the 30s, the 40s, 50s. So I'm dragging that cell that works all the way down to 102, I think, or 103, because we didn't start from cell number one, we started from cell number two. If I do this over here, I think it's maybe one more. What's 588 times 2? So, probably that one. That looks like 588.2. So there you go. That is our full cell number 102. That is our other length. And just for my checking, if I do 5.88 times 2, that's 11.76. So that's now the other end. So that's measuring, if we're measuring from the left tip, if we measure at 11.76 meters, that is all the way to the right tip of the wing. So we do this as you change your values. Um, you're going to have 100. We're doing 100 points as you do this. The next thing we're going to do is we know when we do our diagram, there is a bunch of shear forces that is going to affect our diagram. One of them is a universally distributed load. So to make this simpler, if you look at my example I did here myself, I look at my formula, right? My formula over here has a whole bunch of equations inside it. So to simplify it for you, we're going to, instead of doing it all in one column, we'll do this. This has like 4 different things inside it. We'll do each one of those 4 as a different column, and then we'll just add them together. So it won't look as pretty, as clean as this one, but it'll be easy for you to understand what's happening there. So the easiest, or the one we'll start with, is the uniformly distributed load. So that is this value over here we have, which is the 23,000 newtons per meter. So that means every meter we should be seeing 23,000 newtons. We are doing a similar approach before. We'll call this the shear force. Call this the shear force wing. Shear force W. How we're going to do this is the shear force is going to equal the distance we are from the left tip times the uniformly distributed load. And this is how we would calculate it when we did it by hand. When we did that shear force equation, we had that arrow going. If the shear force is, so if the distributed load is a force going up, our shear force is a force going down. And so we did the same thing. We added up all of the shear force components previously, or we turned it into like a triangle. But for here, we get that distance and we multiply it by the lift of the wing. And if we press enter, obviously it's going to be 0 at the start. We don't want to do autofill yet. It's going to be 0 at the start, which should make sense because that distance is 0. As we drag it down, before we drag it down, we have to lock in some of these variables so they don't move. So the B7 is the one we want to lock in. So we'll press F4. D2, we do want the D2 value to change because as we drag it down here, we're getting the different values. And that's going to be our shear force. And let's just test, if we go to a value that's around a meter, we have, this is 1 meter and 5 centimeters, it's about 24,000. So it's slightly more than this value, which makes sense because that's 24,000 per meter. And if we drag it all the way down the bottom, that should be great. And it's going to be one big, long, like a gradient of what it's going to look like. And I didn't need to drag it through all the rest, but I guess I'll drag it down for a bit. So that's our uniformly distributed load. Um, what if I was to show you what this looks like, just for the start, and I will delete this after because I'm just showing graphically. That's what this is essentially looking like right now. That's the start of our distributed load. And we know that, right? If we get a uniform distributed load, the shear force version of that is a gradient. Then if we look at our diagram, we know we have 3 different locations where we're going to have an arrow pointing down, right? Or we're going to have a force in the down direction, and that is our left motor, our right motor, and our center of our body. So we will call this shear force of the, or sorry, we should call it an engine because we want to be consistent. Let's call this the left engine, so LE, or should we call it engine one and engine two? What do you prefer? I'll call it the left engine then. So LE will be, oh sorry, EL for engine left, and then we'll do shear force ER for engine right, and then we're now going to do shear force of the, just not the, it's the body, but it's actually the body plus the tail. Because remember we were talking about that in our hand example, that where the body is, there's also the lift of the tail is also pushing down. So that one, I'll just write it like that. So these are our three. This, we're going to use an if statement here because we want to show how this shear force is going to be affecting, how this, the force of the engine is going to be affecting the shear force diagram. So what we want the diagram to jump down at a certain point, and we only want it to jump down when that event has happened. So once we, as we progressively looking along the wing, like when we're doing our shear force examples, if we want to look at a location that is after the engine, as we go from left to right, we have that value of the arrow pointing down then. So how we're going to do that is we're going to make an if statement. So equals if, how if statements work in spreadsheet software is we put if and then a bracket, and we're going to say if this certain event happens, do something, otherwise do something else. So there are two options we have. So what do we want to happen? We want to say if this value over here is greater than, if that value over there is greater than or equals to, so the greater than symbol and the equals to, if that is greater than or equal to the distance where the engine is, then we want to count that arrow pointing down in our equations. So where do we find that distance? If we know that YE, what I'll do here, let me just pause this. So I added the image of the airplane because it's going to be easy for me to explain it if I have the diagram up here. So we're progressing along the wing. If we go from this left, once we get to this point over here, we can see that mouse. Once we get to that point over here, that's where we want to start actually counting those down values. So we need to know at which distance this location is, right? That distance, if we know our YW is 5.88, and we know WE is 2.673, so that distance is just going to be YW minus YE. Right? Let's put this over here for now. So because I clicked out of it, I have to do the formula again, but I can do that. Equals if this distance value is greater than or equals to, and let's just do a bracket over here. Let's do this number. This number is going to be that one over there, 5.88 minus 2673. And let's close that brackets. And we do want these to be absolute, so we'll press the F4 button on both of those numbers. And if we actually highlight it, we can see it says it's false, right? You can see false, yep. So if we highlight it's false, spreadsheets does that, which is pretty good. So you can just see, oh, is this thing actually working? And it should be false. At the 0 meter mark, it should be false. Then, can I actually, I want to zoom it without making everything else. That should be better. Okay. Oh, so you have that form over here. So, then, so that's our condition. If this is true, do something. So if it is true, we want it to start rendering, we want it to include the negative force of the shear force going down, of the engine going down. So how we will do this is we're going to say minus, and we need to do minus the force of the engine, or the weight of the engine. So the weight of the engine is the weight of the aircraft, absolute, times this number, 19, and that is for both the engines. So 19 divided by 2, but we have to convert that into a percentage. So 19 divided by 2 divided by 100. So it should make a weight force going down. And so before I finish this, that's what happens. That's what we want it to be if it is over that distance. And what do we want it to be if it's not over that distance, if it's less than that distance? What value do we want this to be? So if we're looking at it from left to right, that arrow that's pointing down the way to the engine, if we're not up to that part yet, what do we want it to look like? What is it? How is it going to be affecting our shear force diagram? It's going to be zero. It's not. We're not drawing the arrow at all when we're looking at it from left to right. So zero. We don't want it to impact it at all because we're not. If we were doing it when we were on the board and we went from left to right, if we haven't reached that arrow yet, we're not counting it. So we just want it to be zero all the other times. And if we press enter, cool, autofill, yep. Now I'm going to have to zoom out here, apologies. But so if I zoom out and, over here, 3.2 meters is where that engine is. And so now saying at 3.2 meters, make our graph go down 19,000, which is like our fast method of doing the shear force diagrams. When we went to that point, we drew an arrow going down at 19,000. Yeah, we're going from the yeah. So if we just hit the shear force at this point, we'd need that's how much of the distributed load. So that's how much up, and this is how much, and then there's a big jump going down from this point. And we want that to be constant for all the rest because it's not changing. But from that point onwards, we're going to have that arrow in our drawing. So we'll do the same thing with the other engine, and for this one, we can start by just copy and pasting the formula because for the bulk of it, it's fine. All we have to do is adjust this part over here of where we want it to count. So this one over here will be B2 minus B3 gives us that distance. Then we want to plus, so this one will be YW plus YE will get us where this second engine is. Right, because if we start here, YW is that wing, plus YE will get us to this second engine. So we just want to change that from a negative to a plus. And now this one, if we go, there we go, it's about 8.5 meters. That's going to happen. And the last one is we can do the same formula because the formula works. Actually, no, we'll do this one from scratch. So for the last one, the body plus the tail equals if this value over here is greater than or equals to. Now, what do I want this distance to be? You tell me. What distance should we want to the shear? Do we want to include the arrow of the weight and the tail force? Where should that be located on our aeroplane? So over here, we're doing the if statement. And that means we're going to have an arrow going down in our shear force diagram. And we're measuring it from the left tip. At what distance should this arrow be that's going down? So it's in the middle, yes. So it's 5.88, which is that cell. So you want to say it's greater than or equal to just that value over there. The reason we do greater than or equals to as well, side note, if you just did greater than, it needs it to actually be greater than. So if you had a distance of 2 meters and the number is 2, it won't work. But we know that it does happen. That's when it's greater than or equals to. And we also do that because you're dividing it by 100. You might be slightly off from the actual value. So we want the graph to be as good as possible. So do great for this particular one. Use greater than or equal to get those values. So if that's where the wing's heading down, we want a downforce, and this downforce will be, we know it's got the lift of the tail. It's going to be affecting it, plus the weight force, right? But not the engines. So we're going to do the weight force times, we want 100 minus 19%. So that gives us the rest of the percentage of the body. And we'll just divide this number by 100. And I've got to make sure now everything is locked in. Locked. Everything except D2. We want D2 to be not locked in. And like in other examples, if it's not that, we want it to be 0. And then we can close that. And then we should be able to drag this down and we should get some values. I should have put a negative, but when it happened, it did happen at the beginning, at the middle, which is correct. But I forgot to put a negative value here. We want it to be a negative minus. Let me just close. Yep, let me just finish the bracket. Zoom in on the formula. If you know the raw values already, you can plug the raw values in. I'm just also doing it in Excel form because why not teach you something be useful later? But if you know, if you just want to be D2 is the one that you can't manually put in, that one you got to base off your table. But everywhere there's a dollar sign, everyone's locked in theory, you can just manually put that value in yourself. You don't have to have it referring to somewhere else on your spreadsheet. So if you said their D2 is greater than, if we know the value is 5.88, so we can put that in, and then we could do all these values with our calculator, we can just do those ourselves. So now if I drag this, we can actually drag all these four and drag them all down. My mistake. We need to make sure our negative is going through. So these are what's happening here, and it makes sense. If we let's just look along the airplane timeline as we scroll down. We start here, everything's at 0, 0, 0. We have this shear force of the wing lift to the left. It's going up, and then boom, we have a drop when we hit our engine on the left, and then the next hit over here we have the center of the aircraft with the body and the tail, and then the third one is the engine on the right. These are our three negatives. So what we want to do is we want to add these all together. So we can say shear force total equals, you can use two functions here. Both of them are fine, depending. If you want the simpler one, you can just say this function plus, sorry, that value plus that cell, plus that cell, plus that cell. You can do that, right? And if you're just, so press the plus button, press the button, plus. That's fine if you have small ones. But let's say you're doing something later when you have like heaps of values and you don't want to have to press the plus for each one. Your other option is you can use the sum option. Sum adds up all the individual things and we can just drag them. So we'll start at brackets and then we say, I want to add up all these three values. And then we close those brackets and that will do the same effect. And then if I press tick to do those selected fields, so now this is the sum value of all of those. And if you see over here, just before here it was 74,000. As we went, it went to 58,000. So it added the 77 minus 19,000. So that kind of works. All right, now we can get our graph out of this. To get our graph, we want to highlight this row and then hold the shift button. No, not the shift, my mistake. The control button. We're going to press the D column, hold the control button, and then press the I. And so now we have those two rows selected. We'll then go to inserts and we want to insert a charts. And wow, that's almost correct. What is wrong? There's something wrong with you. I don't want a line chart. I want a scatter chart, and I want my X value to be distance from the tip. Uh, yeah. Let me get this working, and then I'll explain what I'm doing. Let me view, insert chart. This is not what we want. The x-axis is down there. That's the distance from the tip. Yep. And we don't want, so all we want is the total one. So we want to remove that. Okay, that's almost what we want, except it's in a bar form. And then once I get it working, I will show you how we do it. Okay, all right. So let me show you how we did the chart. I'll show you how I did it, and then you can do the same thing. So we don't have a chart at this point. What we can do is we can highlight this particular row. So highlight just shear force total and highlight if we press our control, we can press D and I, which are our two columns. Insert, chart. Things we've got to change here is we want it to be a line chart because it looks better for our purposes. Don't worry about that data range. That's just going to do the whole spreadsheet, but we stopped at 101, so it's not going to go any further. The x-axis is going to be distance from the left tip. And so we see here we've got this distances now. It's 2, 4, 6, 8, 10, almost 12. This series, we don't want the distance from the tip to be down there because that's what that blue line is. And remember, if you think of that, that's a number from like 1 to 12. That's why it's very low when all these numbers like in the thousands. And then, so we want to delete this one. So remove that. And that is our shear force diagram, which is similar to the one I had in the other sheet, except do you see how this is more steep, this angle here? We know in real life, or in our real example, that's supposed to be vertical. But because we've done 100 discrete locations, that's why it's got that tiny slope there. In my example, right, the slope still exists slightly, but it's more steep because I did 1,000. So for your example, I mean, that's more than enough. That's still great for that case over there. Is the number the same? Yeah, in this example over here, it's about 11,000, sorry, 110,000-ish, I think. So we got that graph. Good. That's the first half done. Next, we have to do the next graph we want to do is the bending moment diagram. Now here we could do the same thing. We could add the bending moment from each individual components. And now that we've broken it up, we probably could. We could find out what the bending moment of each individual area is, or yes. Is it slightly off or very off? Yes, so we forgot a. How low do you go? Do you reach? Is your lowest? How far does your wing go? Does it go to 11 point? Does it go to your full distance? Yeah. Yeah, it should be. Or very, very close. Mine is like basically it's almost zero. Shouldn't be off, but you know what probably is? Your because um you probably rounded your shear force. So you probably rounded your distributed load. But 12, but we're talking about 12 compared to what percentage is that? Less than 1%? You said you're giving me the number 12, right? What's your maximum shear force? Is it like in the hundreds or thousands? Yeah. Yeah. So 100, so you're about 160 and your lowest number is 12, so it's about 10% off. Like I saw your graph. Show me your graph again. Your graph's fairly close to the real one. I would say it's just a rounding error because I got these numbers from formulas themselves, so they're pretty accurate. And even that, I'm still go to 0.0006. That's only to the millionth percent. Okay, that's something up, yeah. Let me draw the graph for the bending moment and then we'll do it. So to do the bending moment, we're turning this into a bunch of little trapeziums and we want to add up the previous distance for that. How I found to do this is if we start over here, we'll start from the cell below the top one because we know the bending moment is going to start at 0. So for here, we want to pretend each of these little triangles are little trapeziums. So what we want to do is we want to get the current cell over here, shear force, plus the previous cell, divide that by 2, so that's getting the average height. That's how we do our trapezium, multiplied by the distance between these two. So it's going to be that minus, so D3 minus D2, and I'll put that in a fractional form again. So that is how much area we're adding, and then we have to add our previous value to this, which is J0. And if we do this, it should go up and should reach a maximum here at 11. And then it should start going down. Oh, hold on, reaches a maximum somewhere else. It reaches a maximum here, 34, and it goes down. And I'm going to do the same thing. I'm going to add this graph. I'm going to press highlight J and highlight D and go to Insert, Chart, and oh, that's a nice looking chart. This axis will be the distance from the tip. We want to get rid of this. And now over here, again, we're going to have the errors of like we're compounding an error in this one because we're doing little areas. The little trapeziums are they're not exact. We know that a derivative of a sloped line is a parabola, right? So because we've done the derivatives in maths or integrals. So we've done integrals in maths. We're doing a very rough version of that. And so because that we've got like this compounding error down here, which is going to be slightly off. And when I look at the graph and even in the HC markings, we know what this graph should look like. We know there's some sort of error, but we can see here that things that we know that exist here. We know it's going to be some sort of curvature going up. And if we zoom into like these components over here, you can see over here that the angle slightly bends, right? And that's where the engine is. And that gives us our second graph, which is our bending moments, our bending moment graph. And then when you're putting them into your report, you can make these graphs look nice and pretty, and you can just copy paste them or screenshot those two and put them into your report. I want to see you do them by hand, and then you can use this as like a verification to see like what the angles. The actual numbers you get here, you can't trust the numbers because the numbers are going to have that compounding error issue. So when you want to actually find what the maximum bending moment is, that's one that's easier for you to do when you know what the graph should look like. We know that this graph over here should look like a triangle plus a trapezium. So we just find the area of that triangle and the area of that trapezium, add those together, and you'll be close to this approximation value, but your value will be more accurate. So I like to use the graph to see visually how it looks like, but you get your own personal numbers that you're calculating yourself. You know the accuracy of those points better. Let me just save this and I'll